it will still put something without any parameter. This is the beauty of R. Look, I didn't give any like extra parameters. So R has taken default parameter to plot the histogram. Okay, so don't be confused that you have to pass all those parameters, X lab, Y lab, then the color, things like that. These are for fancy stuff. Okay, if you want to quick and dirty, you can just use the function at ease. That's why the visualization, I have not touched that in this case, but because visualization look at aesthetics here and there, so I will put visualization as a separate session. But yeah, so you can see histogram could be so easy. Okay, and it is actually plotting the frequency by default, so you can see. But in order to get more custom, more kind of a decent look, we are passing those like extra parameters, like how we want to see, what is the level, color, blah blah, and we got that. So we have finally plotted the MPG data as a histogram. Now, what is the application of this histogram, like this plot, the distribution? Okay, how does it help? What is the mathematical like a uses of this? We just don't plot for the sake of plotting. Okay, we just want to get some mathematical benefit and understanding of it. So now the question is, what is the probability from this population, like from this data set we have, that if I choose a car, the MPG is less than or equals to 25. So MPG, you can see this is the MPG. So I want to see what, if I choose a car, what is the probability I will pick a car or I will get a car which is which MPG, mile per gallon, should be less than or equals to 25. That means I'm looking at a line from here and all the probability density function from up to this, from this way. So I want to check this probability. What is the probability? And that is the area under the curve. And how I get the area under the curve, given this, we use the p-norm function. Since it is a like a normal distribution, so we want to get the probability of this normal distribution, given that the mu like this is I am expecting that value should be 25. Okay, and this is the distribution I am creating over using the mean, and the standard deviation is this one, and the lower tail, because you know this is the lower tail and this is the upper tail, because if you see, this is my mean, this is called lower tail, and this is the upper tail, and I want to get the probability related to the upper tail. Okay, or if I don't tell anything, it is by default lower tail. Okay, by default it is lower tail. So but you can say lower tail. So let's see what is the probability that a car will fall under this probability, and what is the value of the probability. We can say there are nearly 80% chance of picking a car from this car data set which will have a mileage less than or equals to 25. And you can see most of the data is falling under this area of the curve, okay, which we can visually validate as well. But mathematically, this is the implication. Now, what is the probability of a car falling between this range? That means we are talking about a range from this to this, like a start and end. So 30 to 35. Same way, we have to get the area for 35 and then deduct the area from there. Then we'll get the portion of the area between this curve. That's why there's a minus. Okay, so you get a area of first area, then second area, and the difference between the area will be the probability that will be having a car between this range. And we can get that, and the chance is like 4%, which is true because we have only few cars probably here, given this evidence we have, that falls within this range. And that is like visually we can check from this graph, and mathematically the p-norm function is giving us this confidence. What is the probability the car will have more than 25? Okay, that means we are talking about this right hand side of it. So you can also do this way. You can either do this and make it the lower tail false, you will get that value. Or if I write this one and see the probability, you see there is a 20% chance, like less probability comparing to the other probability. That means previously we got 80% and it's a 20%, we will get above 25. Okay, above 25% is like this. We have less data or less area in this area per se. You can say there, if you said line here, and what is the area from there to all the way, less area than the other side of area, which is actually this one. So let's correct that, because this is actually true. But the other way we can calculate it, we can say 1 minus The total area of the probability is 1 and minus the probability we have got here. That is actually the probability, okay? And also the lower tail false. And if you print both of them, this is actually giving us the same value. So 1 minus the probability we have got that it will be above, it will be less than or equals to 25. So deducting that from there, or we can lower tail false, it will get the same probability answer. So this is the application. Or once you say normal distribution, the probability distribution, that's all help us to calculate the probability given an observation will fall within a particular region. Okay, so that is the application. Now we'll see some parametric test, because it's an interesting exercise we'll be doing. Let's look at the data set we have. This is the 5 startup companies data in Australia. So let's read the data like using the reader CSV and look at the data set. It has the like a 50 observations, and these are the R&D spend of a company, a startup company, and these are the administrative cost spend for a year, marketing spend for that company, and the company is located either in Melbourne, Sydney, or Adelaide. These are the 3 states in Australia, and the startup company's profit. Okay, so now we want to make some questions like why is it significantly R&D spend is significantly implying the profit, or our marketing spend is actually like a profit, like what is the relationship? Okay, not the correlation, like how significant the marketing spending is influencing the profit. Okay, that kind of thing, like a t-test. We'll be looking at some t-tests. So look at the data again. The data set is just startup companies data. They have different numerical data set. They have a state here and the profit. So we have 4 numerical data based on a state. Okay, so we can slice the data by a state. We can get the data by a state. We can get so we will get the data, but this is only the categorical data we have here. So now let's do some kind of a plotting. We will use a box plot first. Okay, and what is this? Okay, so first we will be doing a single t-test. T-test is a parametric test, because we assume this data is coming from a normal distribution, and that's why data is normal, and we can do the parametric test. And parametric test requires the parameter, which is we need to know the mean. Okay, so that is a single sample t-test. That means we are looking at data as one single vector. Okay, and what is our hypothesis we are developing? We want to check the hypothesis is no significant difference between the mean and the test value. Okay, so we think that we are arbitrarily fixing a mean value of $200,000 is a marketing expense. Okay, and that is our hypothesis, because we have not seen the real mean. Okay, imagine we have not seen the real mean. We are thinking that population. So what is our population here? Our population in this case, our marketing expense of this data set. So let's print the data. This is our population, marketing spend. These are the dollar value. Okay, like thousands. Now we are arbitrarily fixing a mu, which is like we want to test our hypothesis. Okay, we are assuming that our marketing budget, marketing spend of 200K is actually closer to the mean of their marketing spend we see. Okay, and then let's test the hypothesis. That's a null hypothesis. And in hypothesis testing, there are values called null hypothesis and alternative hypothesis, and there's p-value. If p-value is small, then the null hypothesis will be rejected with a significance level. And ideally, our significance level is always 95%, which is given a significance alpha level called 0.05. So if our p-value is smaller than 0.05, then we reject the null hypothesis. If our p-value is greater than that alpha level, which is 0.05, we retain the hypothesis. That means we cannot reject the null hypothesis. We tell, okay, we cannot reject it. So we have to accept it. Okay, so let's see. In this case, let's do some hypothetical testing in this case. So we want to do a test which is called t-test, which is a parametric test. And how we do it in R, t.test. So take a note, this is t.test, which is actually a t-test on a single vector. because we are not doing there are different kind of t-test which is coming, like a pair test, a pair independent test, then pairwise dependent test, which is coming next. But we are looking at a very simple test, and we're checking the mean is closer the guess we have making here. Okay, and we are making that guess, and let's see what we can find it from. And our significance level is now, instead of 95%, we are giving a confidence level of 99, which is a more, we want to get more confident. Okay, we can say, and we can see it. Now let's do a t-test. The simple formula is t.test. It gives you the data set, and this is the assumed mean you are asking for, and that is the confidence level we are after. So we want to predict, we want to assume, we want to do a test that we want to be 99% sure that our mean is $200,000 should be the mean of this population, and we are making this test. And let's print the test result, and test result is p-value is 0.166, which is greater than what? 0.05. That means we are the null hypothesis will be retained. Okay, so p-value is higher. Okay, that means it is greater than that the significance level. So we cannot reject the null hypothesis. We are retaining the null hypothesis in this case, which is, that means, yeah, the 200 level, 200K is really closer to the mean. And let's validate it. What is actually the mean of this this value? So we can formula mean of our data set of R&D spend, right? No, marketing spend. We can see our mean is similar to 222K, which is not very big from there. But how about if we change it to like 100K and see if our statistics result change or not? So in this case, we are assuming or guessing that our the average expenditure for marketing for those companies is like 100K, and does it fit given the population? And we get the result. We get a result of is 4 into 10 to the power, which is, if you print it non-scientifically, which is this value, 0.000000, which is very smaller. That means we are rejecting the null hypothesis, right? We are, because our p-value is smaller, then the null hypothesis will be rejected. Okay, that means there is significance difference, because our null hypothesis is called there is no difference between the assumed mean that we are thinking and the real mean. But in this case, we are rejecting the null because our p-value is very small. And in fact, this is not true, because we have seen our population mean is actually 222K, but we assume 100K for the sake of checking whether the hypothesis testing is working or not. So we validated, yes, 200 is very closer to the mean, and we are accepting the null hypothesis. But in the second case, when we are assuming our mean is 100K, we are rejecting it because it's not closer, it's very different from the actual mean. So that is the simple single sample t-test. Okay, so this is the significance test to check whether the mean closer to the population mean or not. Okay, that is the purpose of single sample t-test. Now we'll be doing the parametric test, again the t-test, but with 2 independent samples. So here, previously we have seen only 1 sample at a time. Now we are checking 2 samples together. And what is our hypothesis in this case? Okay, we want to check the 2 things. Like we are already taking only Melbourne and Sydney. Want to compare the R&D spend and profit are like a difference based on the state. Okay, so what is the test? No difference. First, our null hypothesis is no difference in the mean R&D expense between Melbourne and Sydney based startups. Okay, that is our null hypothesis. And alternate hypothesis, there is difference. Similar to that, in this case, we are taking a data, 2 sample of data side by side, but they are independent. Okay, that means there is no correlation between the data set. Okay, what is our data set in this case is R&D spend and state. Okay, R&D spend and state. Okay, so they are independent. Okay, so that's why we want to check whether there is any like a significant difference between these two states. Okay. And what we are doing, we have to have some assumptions, and we list how we can validate those assumptions using some statistical test. First of all, we want to check the F test, which is the variance equal variance test. Tells us whether the data is like this is like a var test, var.test. This is R function, which will give us the F score. Okay, not F score, like F test result. That tells that they are coming from same variance or not. So let's take, since we are only after two states, Melbourne and Sydney, because it's a two sample. Although there are three, but we want to give only the two pairs, like a Melbourne and Sydney. But if there is more than one pair, we will go Anova, which is like a more group, like an inter-group kind of things. But here we are, for simplicity, to fit it for the purpose of t-test, we are making a two sample, and the samples are from Melbourne and Sydney. So we're taking that subset from the sample and getting the R&D, and then we are taking a var test related to the spend, like R&D spend across a state, and we the p-value is this. So p-value is higher. That means we are retaining the null hypothesis. Okay, that means they are coming from the same variance. Okay, so there is equal variance. So that second assumption is true from the test. So the samples are independent because you can see Melbourne is Melbourne, Sydney is Sydney. So they are independently taken, and this assumption 2 is they are samples are drawn from population of equal variance, which is our null hypothesis for the var test. We have assumed that, and that is validated here. Now we want to check the data is normal. How we can test that? So let's check one by one. Say first get the data which is related to the Melbourne. So we have subset function. The subset function is actually giving us a subset of the data from our test data, where data is where state is Melbourne. This is we get our Melbourne data. We are getting our Sydney R&D data. Okay, so we are getting our Melbourne and Sydney test data. Now we want to check the normality. There are a few ways we can check the normality, but statistically there is a test called Shapiro test. Okay, this is you have to remember. These are the tests because statistics require some kind of like a memory. You have to remember what test is for what, like a t-test. When you do t-test, when you do Anova, when you do like a rank test. Okay, so these are our like a variance equal of variance test. So this kind of knowledge base you should have if you are working on a statistics. So Shapiro test is mathematically checking whether data is normal or not. But visually you can also check. This is the kind of visual inspection I have written here. Before going to Shapiro test, let's do a visual test. So visual test is actually done by QQ plot, which is called quantile plot. If I open it, you can see this is the quantile plot. If this quantile plot shows it like a linear like this, that is telling the data is normal. Okay, this is called normal QQ plot. So this is the formula for QQ norm and QQ line, QQ norm, QQ line. So I'm plotting both Melbourne and Sydney and putting it side by side using par function. So that par is telling keep the two graphs together is 1 by 2, like a one row, 2 column. That means 2 column here you can see in the graph. So if you say this is the function, this is the way we can put two graphics together. If I don't use the par function, then this will be in one page, it will be in another page. So if you want to keep multiple graphs together in R, you use par function. Okay, so and that QQ plot is actually visually telling this is actually normal distribution. But also Shapiro test can also confirm that from mathematical point of view. You can see the p-value is very, very higher. Okay, so that is higher value means retain the null hypothesis. That means in this case, null hypothesis is the data is normal, and the alternate hypothesis is data is not normal. But since p-value is higher, we are accepting the null hypothesis. And second one is also very big than 0.05. So this in both of the cases, the Shapiro test is telling data is normal, and we also confirm that to visual checking as well. So this is very important because when you try to do any statistical analysis, you want to check the normality of the data. The Shapiro test or QQ plot will be your savior to help you whether data is normal or not normal. Okay, and that is the check. If they find the data is not normal, then you probably try different transformation. And okay, and now we just do this pairwise the independent test. So this is the same t-test, but here
স্যার একটু স্যার এখানে ডাটাটা স্যার নরমাল মানে চেক করার পরে আমরা দেখলাম যে এটা তো নরমাল আছে আর কি। একটা এক্সাম্পল দিলে ভালো হতো যে কিভাবে মানে আমরা ট্রান্সফর্ম করতে পারি আর কি এখানে।
হ্যাঁ, that is coming next. I think I have abnormal distribution somewhere. Box plot. Okay, t-apply. I think I had an example, but I probably removed that. Okay, but otherwise I'll probably show tomorrow, next day, how to transform if your data is not normal, how we transform it. I think, okay, let's see. Can I QQ box plot? Oh, here. This is there. I can see. Okay, I have a transform it to a square root transformation. So I will explain that. Okay, I will show data is not normal in this case, but I will show you. Okay, this from the Anova test. So that is coming next, but let's see where we are. We are here in the okay, here. So now the same t-test, but it is a two sample independent t-test. Okay, so the way we do that, we put the value and the second value as a tilde sign. It's a kind of a formula. So if you write this is the way we can do. The previously we do the t-test with only the t.test, give the sample and the mean that we want to test it. Okay, but here we are using the same t-test, the same function, but we are passing two things with as a formula. We want to check the spend respective to the state, okay, as a data set. So this is the difference of these two functions, the same function, but invoking differently. In this case, we are having a pair, not pair, it's like a two independent sample t-test. Okay, so the independent samples are coming from both Melbourne and Sydney, which is as an state, and the data is the spend. And if we run this, and it will give you the result, which is this. So in this case, what is the p-value? P-value is very high. We are retaining the hypothesis. Okay, this means no difference. There is no mean difference actually in R indices between the Melbourne and Sydney, because all the startup company, irrespective of the state, applying the same. But let's try to do it something like we have another place, Adelaide. So what are the values we have? Say unique. We'll just check if we get the same conclusion or not. State, like a data set. State. So we'll take the Adelaide as our example. We'll check Adelaide versus Sydney, okay? So instead of Melbourne, we'll check Adelaide and Sydney. Adelaide and Sydney, all set, although just the variable names should be I'm not changing it, but the data is changing itself. So we'll get the data here, test data. Yeah, normal. Yeah, same normal. Then test it. What is the p-value? P-value is, yeah, is still higher, 0.53. That means there is no significant difference in R&D expenses irrespective to their state, but we get a different p-value than the previous one. Sydney, we got 9.5. Here we got a 0.55. Yeah, but still this is below the significance level, so we cannot reject the null hypothesis. That means our R&D expense is actually same irrespective to their state. They are the origin of the company. Okay, but you can try some other values instead of R&D expense. You can check the marketing expense could be different. They are significantly different. So you can try that, and I put that as an exercise for you. Instead of taking the R&D expense, we have other variables here in the data set. Like your marketing expense. You can see these are the marketing, and you want to check whether the marketing spend is significantly different between the two states. Okay, you can take that as your exercise, and you can just change some of the parameters in this code and get the result. Now third thing about the t-test, which is the paired t-test. So for example, you have a
স্যার আমি ওইখানে স্যার এখানে বললেন যে মানে পি ভ্যালু তো বেশি আছে আর কি, এই জন্য আমরা মানে এটাকে রিজেক্ট করেছি আর কি। সেটা কি টি ভ্যালু দিয়েও কি সেটাকে এক্সপ্লেন করা যায় যে মানে টি ভ্যালু স্যার এখানে 1.96 এর কম আছে, আমরা কি ওটা দিয়ে এক্সপ্লেন করতে পারি?
না, যে পি ভ্যালু,
হ্যাঁ হ্যাঁ স্যার, এই যে টি ভ্যালু যেটা আছে 0.62, আমরা কি এইটা দিয়েও কি এক্সপ্লেন করা যায় যে এটা কি 1.96 এর কম আছে?
or t-value. Now, t-value is a t-statistics that is actually different. Our significance test is always considered with the p-value. t-value has a different interpretation. t-value হলো যে t-distribution এই ডাটাটার given this number of like a degree of freedom, that is the t-statistics. A t-statistics has a different interpretation. I don't exactly remember exactly now, but that is telling given the degree of freedoms and sample size, আমাদের টি স্টুডেন্ট ডিস্ট্রিবিউশন কার্ভে টি ভ্যালুটা হলো এত, যে যদি কেউ ম্যানুয়ালি এটা ক্যালকুলেট করতে চায়, ঠিক আছে, তাহলে ওই একটা চার্ট থাকে, সেই চার্টের মধ্যে টি ভ্যালু কত, ডিগ্রি অফ ফ্রিডম কত দেখে উই ক্যান নো দিস ভ্যালু অফ দ্য পি ভ্যালু। ওকে, সেটা থেকে কেউ যদি they don't want to accept it, they want to take a manual calculation, say a t value, degree of freedom দেখে, there is already a standard published chart, সেই চার্টে এই ভ্যালুটা দেখে we can manually calculate. But আমাদের এই ক্ষেত্রে টেস্ট রেজাল্টের ক্ষেত্রে we always look for the p value, the significance value. This has to be less or higher than the set value. So 0.05 or 0.01, if it is our significance level is 99, then our alpha value is 0.01. Okay, or if our significance level is 95%, then our alpha level is 0.05. So eketre higher p value means we keep the null hypothesis. That means in this case there is no difference. Okay, a null hypothesis always tell that there is no difference, but alternative hypothesis there is a difference. That means they are not same, they are coming from a different population. In the population statistics, null hypothesis is always telling they are actually coming from the same population, they have the same mean, they are the same parameter. Okay, that's why it's called parametric test. But alternative hypothesis, no, we don't believe that, and we are validating or accepting or rejecting through the p value. Okay, now the other scenarios, sometimes we may have a paired value, which is given previously we seeing the one number across independently different scenario, but now we want to see whether the two pair of values, okay, kind of a before after situation, or could be like a one is the intervention to see the reflection on other. Okay, so that kind of situation you have a kind of a pair sense. Okay, you put this intervention, you get a result, and you want to check whether your intervention and result has a significance effect or not. Okay, if that scenario is there, in this case we are having some marketing spend and we are expecting some profit. Okay, so as generally speaking, marketing spend should be correlational with the profit, right? But how significantly that is actually driving it, you want to test it. So that is the paired sample t-test. The purpose of the paired sample t-test is you have a kind of a pair data, which is a kind of a related data, and we are checking it. So in this case, we are checking it through the marketing spend and the profit, okay, across all these states, where here there is no discrimination. So we are taking data as a whole, data set marketing spend as big data set, and then data set profit is another data set. These are the paired data. So looking this versus this, this versus this, this versus this as a pair, and then we are looking this each pair and making a significance test like this. So in this case, our test is there is no significance between the R&D spend and profit. Okay, they are coming from the same, they are having the same mean, but there is difference. So look, if our mean is actually, we are setting some values here. So our t-test, and the key difference is the pair. That means the data we are setting, we are telling the data is paired, okay, and take it from both sides of the tail, like both alt is like alternative hypothesis, which is look from both of the tail, like not from the one single sided tail. Look at both, like it is significantly different from both sides of the probability density function. So if I run this and you see the result, we can see it is significantly low. Okay, that means we cannot we reject the null hypothesis. Okay, so we cannot accept the null hypothesis. That means it is telling, yes, we find this is significance, there is significance relationship, or there is significance intervention has been applied, and we can significant like a relationship has been found between the expenditure, R&D spend, and the profit, and which is like a plausible, which is rational, right? Kind of if you spend more R&D, you are expected to get more profit, and that is validated from this data set. It is a genuine data set from a startup company. So yeah, as your R&D spend is there, and there is significance, there is a difference between their relationship, and it is validated from two sides of so 2 point. And then it is their marketing spend. Look, is it same for the R&D spend or not? Because we have two kind of expenses. One is the marketing, another is the R&D. Look, if we are curious to know about the R&D as well. So R&D is also telling a significantly, yeah, it is 0.000 something, because minus 2 to the power 16, which is very, very small value. Means in this case, we are rejecting the null hypothesis, because lower p-value is always indicating you have to reject the null hypothesis, okay, and accept the alternative hypothesis. So in this case, it is also telling, hey, yes, R&D spend is also having positive intervention or negative intervention. We don't know, because we don't know the direction of correlation. We know they are significantly related with each other. That if you want to know the relationship between these two variables, we need the correlation analysis. And the direction of correlation could be like R value. It goes from -1 to 1. If the direction is, if it's increasing, increase the profit with the increase of the spend, then you get a positive R. Otherwise, you get a negative R. So now we'll go to the Anova. So in this case, our data set was only for 2 groups. But how about our groups are many? Okay, then many group, still data is normal, or if not normal, we will make them normal. Somehow data is normal, and we know the parameter because it's a parametric test. Then Anova applies. Okay, and how we can do Anova in R, we'll see there are many ways, like a few ways we can do Anova. First, let's get ourselves familiar with a new data set, because it's not only the 2 types of categories. There are 1, 2, 3, 4, 5, 6 type of data set. Okay, so this is the data set we have got, which is on the library data set. When you install R, by default that comes in this data set. So we are loading that data through a function called library. Now this is actually a new command for you now. If we want to add anything that we need to load to our the session, that library, we have to put library command. So library data set, if we do that, then it loads all the necessary data that are available on R automatically in our memory space. And one of the data is called insect spray. It's a kind of pesticides data. So if you load the data, because that is part of this data set, so you just load the data and now load the data onto memory. So that means when you put the data command, then it knows that there is available of this the resource, because we have loaded that library, and from the library we have got this data. Now if you want to see this data itself, what is the data look like? This is, but this is not actually a good way of seeing this thing. You can do what happened? You can do a command like a view, capital V-I-E-W view, and then if you put the data set is in sprays, you can view that in like a table format here. So it is telling the count and the spray type. Okay, there are like A, B, C, D, E, F, G. So there are different kind of insecticides, and these are the different insecticide A, B, C, D, E, F, and these are the different count. Like a insecticide A has been used this many times in different occasions. We don't know the context, but these are the count we have in the data set. Just imagine this is our information we have. Okay, now we want to check whether the uses of which one is better. Okay. In terms of this data. So let's visually we check it. First, we plot this data in a, we'll plot it with a QQ plot, see if the data is normal or not. So we've just put the 2x3 column, so you can see all the graphs in one place. Remove these graphs, And now for using for loop, since we know there are like a B, C, D, E, F, G, and for each of them, we get the data and we put them and we put the QQ plot, okay? And we are making a, oh, because I have not run that. And then we run this. So you can see all the graphs has been plotted here. So A, B, C, D, E, F. You can see some of the data are not actually fitting the lines, okay, here and there, something. So that means this data is not normal because it is not 100% aligned. It's like a few are off scaling. So that from visual inspections, we are checking this data is not normal. And I leave the exercise to you. You can do the Shapiro test on this data set to check whether the statistical result also you get the same result or not. And then we also try to see the box plot. So we just try to box plot of all those things to get more visual interpretation. You can see the box plot. You can see the, the box plot. You can interpret the box plot. I assume you understand box plot. What is a box plot? It has actually the quantile, like the first quartile. This is the mean, and this is the whiskers. Okay, this is the quartile 1, quartile 2, quartile 1, 2, medium, and then the quartile 4, and this is the whiskers. Then this is the mean. This is the mean. So spray A has this mean. Spray B has this mean. You see there's a different means. So from visually, we can see the means are different. So without any statistical test, we can tell within this group of these 7, 1, 2, 3, 4, 5, 8, 3, 4, 6 groups of things, they are significantly, their means are different. But can we statistically tell the difference of their means are significant or not? That is the question in our test. Okay, the Anova is going to tell this answer. Okay, Anova is going to tell whether the means are significantly different among this group. Okay, it's not only 2, we are talking about in this case 6. So that is the parametric test for Anova, which is telling us the answer. Visually we can see that, but how statistically? We don't believe in the visual. We are blind people. We want to see the number. But you can see there are outlier. These are the outlier, and which is probably causing our things to get off scale, not like some anomaly. Okay, that's why we would try to transform the data and make it more normal. So this is the transformation. So we do the square root transformation in this case. Okay, so we do the square root transformation of those count, and we do it here. And now with this square root transformation, we are plotting the data again to see if the data looks more bit normal, okay, or not. Yeah, still there's some, but it has improved a little bit from the previous situation. Now, and we also see the box plot. It should, yeah, it has improved because it has got some kind of, still we have on outlier, but it has some kind of the spread has reduced. We don't have much differences. Now, how we can do the Anova? So the Anova, there are several methods in R. So showing the method 1. Method 1 is one-way Anova test. Okay, that is the way, one-way dot test. So if you want to look the manual, because this is coming from any other statistical package, one-way test. This is the one-way test, which is one way of doing Anova testing. Or there is another function called Anova, AOV, Anova, AOV, analysis of variance, okay, which is the Anova, analysis of variance model. So there are 2 ways, and actually there is another way, third way, which is a logistic, like a regression model. I think I didn't put it here just for simplicity. Yeah, just put only 2 methods back. So look how the test is actually doing and what we get from the test. So first of all, this test is telling, okay, we want to check the transform value, which is already a square count. So we are not taking the count as a raw value. Yeah.
স্যার আপনার কি ইফতারের টাইম হয়ে গেছে কিনা? ওখানে তো আজান হয় না অস্ট্রেলিয়াতে।
রাইট, আর একটু কিছুক্ষণ বাকি আছে। হ্যাঁ, আমি তাহলে আসলে কি কুইকলি শেষ করে দিতে চাচ্ছি জাস্ট এটার পরে, and I have left the solution. আমার আর 7 মিনিট বাকি আছে ইনফ্যাক্ট। ওকে, তো we are taking the raw value, square count of a spray, and running the test is telling p-value is less. Okay, that means we are rejecting, p-value is lower, that means we are rejecting the null hypothesis. What is a null hypothesis? Null hypothesis, there is no difference on the mean. That means we are rejecting that. That means we are we are telling like there is differences, and visually we have seen that already. Okay, but look at the second test. The same, we are taking the square root and the pairwise, and then you can see we also get the similar rest, and this is statistical significance. The 3 star means this is a statistical significance result, and this is actually this, and we are still get the same conclusion from the first test and second test. Okay, but now in order to know which group is actually significant, okay, among the group, to know the intergroup interaction, okay, we need to do another test which is called Pairwise T-Test. Okay, and we can see this one. You can see the mean of individual group. We can see the mean of individual group. A has mean B, B has C. So you can see there are different means of each group. Okay, that means some groups are really different. Some groups are not. So we can find that using the pairwise T-test. So pairwise T-test will help us to get that answer with the Bonferroni method. So that's called the post hoc test. Okay, and that post hoc test, pairwise T-test, give us that idea. So A and B giving 1, which is very higher. That means we cannot, there is no significance difference, okay, between A and B. And we can see that. You can see the mean difference between A and B is not significant. So that's why it's 1. It's very high. We cannot, we retain the null hypothesis for A and B. But for others, there are A and C significantly different. Okay, this is how we can say intergroup whether the differences between the groups are significant or not using a post hoc test. Okay, so with this, I leave the code with you. I have already emailed the code, and this lecture slide will be there as well. So I sincerely request you run those codes by yourself, do some changes here and there, because there are a lot of variables in the data set. Take any of the variable of your interest and try to do your own. And next time we will do some non-parametric tests, which I have not covered today. So we'll see few non-parametric tests next day with some visualization. So with this, I would like to stop here and pay my huge thanks. And once again, salam to you and make dua for me. And I wish you all the best and happy Ramadan. Okay, আমি এখানে শেষ করতে চাচ্ছি এখন।
Happy Ramadan to you.
Yes, yeah. So আশা করি আপনারা সবাই এই আর ফাইলটা পাইছেন। না হলে এই অনিক বা এই মুস্তাফিজ ওনারা এই আর ফাইলটা পার্টিসিপেন্টদের শেয়ার করে দিলে দেখেন। ও গুড, তাহলে আমি রিকোয়েস্ট করব আপনাদের যেহেতু সময় আছে, ইউ ট্রাই টু রান ইট বাই ইয়োরসেলফ। এন্ড আমি আরএস ফাইলের সাথে সাথে আরো ডাটাগুলোও পাঠিয়ে দিয়েছি, কারণ ওই ফুড ব্লগ, তারপরে এই যে স্টার্টআপ কোম্পানির ডাটাগুলো ছাড়া আপনারা তো কাজ করতে পারবেন না। সো আই হ্যাভ অলসো ইমেইলড দ্য ডাটা সেট অ্যাজ ওয়েল। সো পুট দোজ থিংস ইন এ সেম ফোল্ডার হোয়ার ইউ আর ওয়ার্কিং। ওকে, and if it is not working, the way you go to the file and go to more, set as working directory, put that set as working directory, make sure your all files are in the same directory and put set as working directory. Otherwise you may get like the file the CSV file you are looking is not present because the directory was not set. Okay, so just remember, you go to the files, keep everything in one folder, set as working directory.
So kind in the GIS is the add folder, kind of.
Yeah. So this is the way. I think I stopped sharing, so I just quickly share and then I'll log out. So this is the way you go there, you put your files everywhere, more, click on more, that icon, then set as working directory. Okay, then it will be referring every file in the same directory. Okay, so then if you read a file, any file with the same directory, it will be there.
Thank you, sir.
Okay, thank you. Yeah, okay, I wish you all the best. Okay, Allah Hafiz. Assalamu alaikum.
Allah Hafiz. Assalamu alaikum.
আসসালাম।
আমি হচ্ছে যে গুগল ড্রাইভটা আপডেট করেছি, আপনারা একটু চেক ইমেলও করা হয়েছে। আপনারা যেটা করবেন সেটা হচ্ছে যে আপনাদের ড্রাইভে ঢুকে শেয়ার উইথ মি এখানে আসলে পাবেন আমাদের যে ট্রেনিং এর টাইটেল আছে ডাটা ইনকোয়ারি 22 আরজিএস আর এন্ড এন। চেক করবেন। ইন দ্য মিনওয়াইল এলএমএস আছে, এলএমএস ও ম্যাটেরিয়াল গুলো আপলোড করা আছে, অডিও ভিজুয়াল গুলো বাদ। যদি কোনো ডিফিকাল্টি হয় আমাকে জানাবেন। আমরা আজকের মতো ক্লাসটা শেষ করছি এখানে। নেক্সট ক্লাস আমাদের সেশন হচ্ছে আগামী শুক্রবার। বিফোর দ্যাট উইল গিভ ইউ দ্য আপডেটস। আসসালামু আলাইকুম।